Hi, I'm Mengliang Zhang. Our project is expanded field survey and sampling techniques for the polychlorinated biphenyls and the dioxins. Our project is done by Dr. Glenn Jackson and me. This project is supported by a grant to Ohio University from the Department of Energy. Our purpose of this project is to test the polychlorinated biphenyls in the soil matrix at Paul's, Piketon, Ohio. Now I'm demonstrating the field analysis method for the determination of polychlorinated biphenyls using this portable gas chromatography and mass spectrometry instrument, and with the headspace solid phase microextraction technique. First, we switch on the instrument. It will take about 3 minutes to get ready for analysis, which is very convenient for the on-site analysis. And we can control. There are two options, two software we can use for this small instrument. So from this small screen, for the general analysis, we used a Smith GUI to control the instrument. And for the method development, we have another software. So right now I'm opening the Smith GUI. So after we start the instrument, it will establish the vacuum and the temperature. So this will take like 2 or 3 minutes. And at the same time, we can connect this instrument with the laptop with this normal cable, Ethernet cable. Also, we can see the real-time status of instrument using the small software, which can monitor the screen. It has the same screen on both sides. So this is the rechargeable battery. Here, it can last for 6 to 8 hours. It depends what parameters you use. And this is the small helium gas cartridge. We have another spare one. So this one. So it can use for about 100 runs in our case, because we have a longer GC program. So this is the gas cartridge.
Very good, good.
So we have Cowline standards, which has 13 mixed standards inside. We have a standard spectrum. So these standards are used for the validation of the instrument. So these are the standard spectrum. We can use the intensity information to verify if the sensitivity of the instrument is good. Also, we can use the mass spectrum to check the mass resolution, the mass accuracy. So this is basically what we use for. And we have the extraction solvent here. This one is the 0.2 mole potassium magnate solution in this small vial, and in this big vial is 6 mole sulfuric acid solution. So we will use both solutions for the extraction of PCBs. And here are our soil samples. This one is the blank sample. Sometimes we use this blank sample to verify the system, if the system is clean or not. Or actually it's a blank before the real analysis. And this is the real field sample we got from the lab. And we will use this 20 milliliter spinny glass vial, and it comes with the specific septum and the caps. We will use this clamp to seal the caps for this glass vial. And this is the heating block designed by us and with the help of French in chemistry department at Ohio University. So the temperature is monitored by this thermometer. We use 100 Celsius degree to do the extraction. Okay, so from the screen you can see the instrument is ready to go. Usually, first we run a system blank, which means we didn't inject anything, to just run the whole program and to see if there's something in the column to check the system if the system is clean or not. So we usually just click yes, we run a system blank. So we can just start run, click start run, and the system blank will run immediately. So from this screen, all they are the same. You can see the signals, and also we can. There's another software we can use in the laptop to monitor the real-time gas chromatography and the mass spectrum. First, we connect the software with the instrument. So you can see almost the same thing. And on the other page is the mass spectrums. We can see the real-time mass spectrum here. Even in this small screen here, we can also click. It has a split screen which shows both gas chromatography and gas chromatogram and the mass spectrum. The gas chromatogram is on the top, and the bottom is the mass spectrum. So it will take about 2 minutes for the system blank, and then we will use these Cal-Line standards to validate the instrument. So first, I want to introduce a little bit the swimming syringe. It's a special design swimming syringe with a special protective cover, and it works like a ball pen. We can just press the plugger, and the spinning fiber will expose, and then it can withdraw by plugging the plugger. So we do this extraction. We just insert the spinning syringe and expose the spinning fiber for 30 seconds. We have a stopwatch here, and we can check the extraction time, about 30 seconds. So after 30 seconds, we inject the spinning fiber into the injection port of the instrument immediately. So we go back home, and this time we don't run a blank, we run a sample. So we can click start one and insert the spinning syringe into the injection port and plug, and dissolve about 5 or 6 seconds, and the instrument will tell you it's time to remove the syringe. Then that's the whole procedure for the injection, and then the instrument will analyze the analyze on the fiber. So you can see from the screen some peaks are coming out. So like I said before, by comparison, our spectrum with the standard spectrum, the standard program, we can validate the sensitivity of the instrument and the mass resolution or mass accuracy of the instrument. So the portable instrument, when we do the injection, the portable instrument knows we are doing the injection because the metal surface is connecting with the 3 sensors on the injection port. Here are 3 spots which can monitor the status of the injection. So after the small sensors contact with this metal surface, it will know it's beginning to do the injection, and after several seconds, it will tell you it's time to remove the syringe, and it's time for the analysis, the GC-mass analysis. So the Cal-Line standards was done, we can use a post-run software to check our data. For example, here. That's hard to see. So this is the sample we just ran, and we can click each gas chromatogram to see the mass spectrum of each peak. So we can compare that peak with the standard results to check the status of the instrument. So that's how we validated the instrument. So right now it's about 10 minutes. We have done the system blank and the validation of the instrument. But usually for the benchtop instrument, after switching on, it will take about at least 3 or 5 hours. Usually we use like overnight to establish the vacuum of the instrument. So, and for the validation of the instrument, it takes like half an hour to run a whole GC program, right? So right now we only use a short GC program, which is only about 2 minutes. So that's very convenient for the on-site analysis. So after the instrument is validated, we can do the real, we can analyze the real sample. So this is the particle scale we use to measure the sample, the soil samples. We place the scale in a plate ground or plate bench. So we turn on the scale, and we use the 20 milliliters glass vial. We put the glass vial onto the scale to tare the weight of the empty vial. So tare the weight. Then, for example, we measure the real sample. About half gram of soil are measured. So this is much less than half gram. We have verified that the water content in the soil doesn't affect the extraction efficiency of our method, but it will affect the calculation of the final concentration of PCBs in the soil sample. So theoretically, we'd better use a dry soil sample to make sure the final concentration of the PCB is accurate and it's easy to compare different soil samples. It's about half gram of soil sample, and then we spec spec 2 milliliters of potassium magnate solution into this sample, this glass vial. Then we add 250 microliter of 6 mole sulfuric acid into the same sampling vial. So that's all the solutions we need for the extraction. Then we seal the vial with these caps using the clamp. Okay. So we shake vigorously to mix the soil with the extraction solvent, extraction solution. then place the wire into this heating block. This heating block can handle like two sizes of vials, which we can use like 10 milliliter glass vial, and also we can use 20 milliliter glass vial. Then we insert the steamy syringe into the steamy syringe into the glass vial and expose the steamy fiber in the height space of the sampling vial. The temperature was set to 100 Celsius degree. Currently, we need extra power supply to supply the power for this heating block, and also in the future we will use like a car battery to supply the power for the heating, for the extraction. Also, right now we are using the regular thermometer to monitor the temperature of the extraction, but in the future we will use like an electronic thermometer to monitor the temperature for the safety reason instead of this regular thermometer. The extraction will take 30 minutes. During this time, we can change the method of the instrument because we use another method. The method is different from the validation of the instrument. So we go back to the home page. So after 30 minutes, we withdraw the steam fiber back to the needle and take the sample, and we inject the sample, the steam fiber, into the injection pot immediately. For the PCB samples, the desorption time is 1 minute rather than 5 or 6 seconds. Because the PCB is not that volatile, we want to make sure all the PCBs on the fiber can dissolve and comes into the GC column. And the desorption temperature is 280 degrees, which is the maximum operation temperature for this special steamy fiber. It takes 7 minutes for the single analysis of PCB samples. After 7 minutes, we can analyze the results using our PostRun software. And in this window, in this screen, we can see two groups of peaks. The first groups of peaks are the PDMS peaks, which are coming from the steamy fiber and the septum. We can consider that the background peaks, we can ignore them. And later is a bunch of PCB peaks coming out. And we can zoom in those peaks and check the mass spectrum for each peak for the identification purpose. And also, according to the instrument response, we can use those information for the quantitative analysis. That's how we analyze the PCB samples in the soil. And after this is done, we can just turn off the instrument and take the instrument to the other side for another analysis. It will take only several minutes for turn off the instrument and turn on the instrument back. So also we can take the instrument, if the site is not too far away, we can take the instrument which is on and to the other side. Right? Is that okay?
Yeah.
I have demonstrated the field analysis of polychlorinated biphenyls in the soil matrix, which concentration is higher than the 10 part per million. And we found that this instrument is suitable for the determination of trichloroethylene in the water matrix. Because trichloroethylene, TCE, is the most frequently reported organic contaminant in water matrix, we developed our method to determine the TCE in water matrix. For the determination of TCE, we do not need the external power supply to heat the vial, because we found that the higher temperature we used, the lower extraction efficiency we achieved. The other advantage to use our portable instrument to determine the TCE is there's no need to use any oxidizing agent such as sulfuric acid or potassium permanganate. For more information, please go to the postfuture.com. Thank you for your time.